Good morning. So, today we will extend yesterday's discussion on continuous random variables. So, just to recall what we discussed in the yesterday's class, I will bring up some key results before proceeding further. Okay. So, some of the key results of yesterday's discussion was if you have the case of discrete random variables, then you basically have a set of outcomes which are discrete. So, the outcomes could be x1, x2 all the way to xn, okay. And the probability of each outcome, if it is summed over all possible outcomes, is normalized to unity, okay. So, this is the normalization condition, and these p of xi are basically probabilities. Okay. In the context of continuous random variables, we saw that the set of outcomes are not discrete numbers. They could be, let us say, between some, it could be a bounded interval. So, our random variable would be between a and b, okay. A is some continuous variable, and in that case, to say that the probabilities are properly normalized, the equation that I have written on the left becomes an integral, where the lower limit is the lower limit of the random variable a, and the upper limit is the upper limit of the interval, which is b, p of x dx, and this is 1. Okay. Here p of x is not probability, but is a probability density function. So, this is the difference. This is now a dimensional quantity. We are also calling this as PDFs. Okay. So, this is a dimensional quantity, has the dimensions of 1 upon x, and the notion of p of x is basically the following. From probability density, you can derive probability as you can call p of x dx as the probability. Now, this is a probability, this is dimensionless, okay, because p x already has a dimension of 1 by x. So, p x dx is a probability which is dimensionless, probability of finding a measurement in the range x and x plus dx, okay. That is the interpretation of p x dx, okay. P x dx is the probability, not p x itself. So, this is the important distinction that we made in the context of continuous random variables and discrete random variables. Okay. Now, we can use this to obtain average of any function of x For example, if you are interested in average of x square or average of x cube or average of any function of x, okay, let us say f of x. Now, x is a random variable which is distributed with the PDF p of x, okay, and I want to know what is the average of some function of x. Okay. So, this average of some function of x is given as the integral of px fx dx. Okay. This is the definition of average of function of x. So, if you take for example, f of x as x itself, this gives average of x as integral a to b p of x x dx. Okay. And if you take in the following way f of x as some power of x, let us say x to the power n, then the average of f of x would simply be the average of x to the power n, which by the definition of averages is integral a to b p of x x to the power n dx. And the language of statistics, this is called as the nth moment of x. Okay. So, it is like the average of the nth power of x, called as the nth moment of x. Fine. So, today we will discuss some important mathematical laws that allow you to derive these moments with a different route. Sometimes the method of obtaining these averages by a brute force integration may not be feasible. Okay, we will give you some examples where the technique that we are going to develop would make life much easier for you if you want to compute the nth moment. Okay, so this is one way to compute the average or the average of the nth power, which is also called as the nth moment of a random variable. So, let me record it and we will compare this with the okay. So, this is the formula for the nth moment, and today we will discuss an alternative formula, one that is more powerful, through the method of generating functions. Okay. So, I will discuss the method of generating functions, and I am going to discuss method of generating functions to compute both the moments and cumulants. Okay. So, I will describe what are cumulants in a short while. Okay. So, the generating function of moments is nothing but the characteristic polynomial. Okay. So, this is nothing. So, the generating function, now this is called a generating function because it will allow you to generate moments of a random variable, is the characteristic function, also called as a characteristic function of the PDF, whatever PDF. Okay. So, suppose you start with I will take an example. Suppose you have a random variable x, okay, and this is distributed as the PDF of this random variable is p of x. Okay. So, you have a random variable x and it is distributed as p of x, that is the distribution of this random variable. Now, to compute mth moment, we first compute the characteristic function. Okay, so first we will compute the characteristic function, which is nothing but a Fourier transform of the PDF. Okay, so this is the definition. So, characteristic function, I will call it as a Fourier transform of the PDF. So, our P of x is transformed to P tilde of k, where tilde here just denotes that this is a Fourier transform, an amplitude of original function P of x. So, you can take the Fourier transform as the following. So, let us say our random variable x is distributed between minus infinity to plus infinity. Okay, so that is the range of my random variable, and so I am going to take a Fourier transform of this random variable. So, this would be e to the power minus ikx dx. Okay. Now, if you look at the definition of average of a function, this is nothing but the average value of e raised to minus ikx. Okay. Since we are using the definition that a function's average is given as integral minus infinity to plus infinity, the function into px dx. Okay. So, this characteristic function is nothing but the average value of the complex exponential e to the power minus ikx. Therefore, I can write down P of k as summation I going from, let me change the variable here, summation I going j going from 1 to infinity e to the power minus ik to the power j x to the power j over j factorial. Okay. And you can clearly see that this is nothing but the averages are simply going to walk over the constants, and what you get here is nothing but summation j going from 1 to infinity minus ik to the power j upon j factorial into the average of x to the power j. So, now you can clearly see that this is the coefficient in the expansion of the characteristic function P of k. And so, if I want to extract the mth moment from this power series, the extraction would require just taking the mth derivative of my characteristic function with respect to ik, and then evaluating this derivative at k equals to 0. This would precisely give me the this would eliminate the coefficient, and what will give me is basically the mth moment of the random variable. So, now you can see that this method, now we can see that this is called as a generator of moments. So, this P of k is called generator of moments because the left hand side is a moment, and by taking the mth derivative of this moment generating function, I can obtain the mth moment, which is this. Hence, that is the reason why this is called as the moment generating function or characteristic function, right. So, So, this is if we compile everything that we have now is basically what we have just derived is basically the formula that the mth moment of a random variable is the mth derivative of the characteristic function at k equals to 0, and this is equal to the brute force integration of weighted integration of our mth power of the random variable. So, whether you want to use the definition which is on the extreme right hand side, or you want to use the definition that we have prescription that we have just derived, it is up to you. It depends on the problem at hand. Maybe in some problems the brute force integration is easier, but in some problems where integration becomes difficult or if m becomes large, you would want to take derivatives of the generating function, because taking derivatives, successive derivatives is easier definitely compared to taking computing integration by parts if m is large. So, these are the benefits of a characteristic function over a brute force integration. Now, one can also generate cumulants. Okay. So, cumulants are important objects, and they are defined as basically they are connected with the correlations in random variables, and I'll just give a definition of defining logarithm of the characteristic function as the generator I think it is better to first write down logarithm of p of k, and then we will introduce the definition. It is perhaps better that way. Okay. So, you can now turn your attention to logarithm of p of k, and I am going to tell you that this is also an important, very important object, and it will become clear in a moment why this is important. Okay. So far we have found a formula prescription to generate moments from characteristic function. Let us see what is logarithm of a characteristic function, okay, ln p of k. So, let us denote this logarithm of p of k as some function of k. We know it is a function of k because p of k is a function of k. Now, if I want to expand this in power series, okay, I can write it as f of 0, that is the leading term, I am expanding around origin, plus minus I k. So, I am expanding in powers of minus I k times f prime at 0 plus minus I k to the power 2 f double prime 0 over factorial 2 plus minus I k to the power 3 f triple prime 0 upon. So, the right hand side is basically expanding in powers of minus I k. Okay. And then if I ask you to associate these coefficients of the expansion as f of 0 is basically if you see, this is nothing but ln of p of 0, which is nothing but ln of 1, because p of 0 is 1 and that is nothing but 0. So, this the leading term is 0. So, what we have here is basically ln of p of k, the left hand side, as minus I k into f prime 0 plus minus I k to the power 2 f double prime 0 upon factorial 2 plus minus I k to the power 3 f triple prime 0 upon factorial 3 and so on. Okay. So, if you denote these coefficients as the first cumulant, let us call them as denote them as some cumulants. At this stage they are just variables to you because I have not really defined physically what is a cumulant. F double prime as a second cumulant, F triple prime as the third cumulant and so on. So, nth derivative at 0 would be nothing but the nth cumulant. This way our series becomes logarithm of p of k as minus I k into the first cumulant plus minus I k to the power 2 into the second cumulant by factorial 2 and so on. So, I can write this as a series as a summation some j going from 1 to infinity minus I k to the power j x j c upon j factorial. Okay. So, now we can see that I can extract any jth cumulant by simply taking derivatives of the appropriate order. So, extracting any mth cumulant here becomes extremely straightforward. All you have to do is just take derivative, mth order derivative of the left hand side, that eliminates the coefficient, and you can write it down mathematically as d to the power dm by dik to the power m ln p of k, and this is evaluated at k equals to 0. Okay. So, this is then classified as, so that is why we can say that ln p of k is the generator of cumulants. Okay. Now, so far cumulants are again these fictitious objects which have not been related to any physical observation. So, we will now connect these moments with cumulants, and natural meaning of these cumulants will automatically arise. So, let us find out the relation between moments and cumulants, and you will be surprised to see that some of these cumulants you already know. Okay. So, this is going to be my first agenda. Okay. So, let us find out the first cumulant. So, the first cumulant is nothing but m equal to 1. Okay. So, that would be just the first derivative. Okay, if I want to use the previous definition, it is just the first derivative of ln p of k. Okay, which I know is nothing but 1 half upon ln p of k derivative at k equal to 0. So, this derivative is nothing but p of k into d p k by minus I k, and this is entirely taken at k equals to 0. Now, characteristic function at k equal to 0 is just 1. So, this is nothing but d over minus dk of p of k at k equal to 0, which is nothing but my, by definition it is nothing but my mean. Okay. So, the first cumulant is nothing but the first mean. This is the relationship that we got. So, at this stage it is not very exciting. Okay, the first cumulant is nothing but the first mean. Let us compute the second cumulant. So, the second cumulant by this definition, okay, the definition which is here, this is the definition of the mth cumulant. So, if you put m equal to 2 here, you get the definition of the second cumulant. Okay. So, let us use this definition to our advantage. So, we can write this as d square by d of minus I k the whole square ln of p k at k equals to 0. Let us find this out. So, we already have the first derivative extracted. So, this would be just the derivative of 1 upon p k into d by di k of p of k. Okay. All this are taken at k equals to 0. So, let us take the second derivative. This would be minus 1 by p of k the whole square, that is the derivative by parts, into d of p k over minus I k plus 1 upon p k of the second derivative of the characteristic function. Again, this has to be evaluated at k equals to 0. Now, if you look at the formula for moments, which is given here, over here, let me circle this formula. Okay. You use this formula for the moments. What you have just written becomes, sorry, it would be a square here. Okay. This becomes just minus of square plus, you can also write it as average of the second moment, or second moment minus the square of the first moment. So, this is familiar, and we could derive it because the value of p of 0 is nothing but 1. So, this is also called as the sigma square or the variance. Okay. So, what you have just derived is basically the variance of the random variable x. So, the second cumulant is now a physical meaning of the variance of a random variable. Variance would be basically a measure of width of the random variable about the mean. Okay. Similarly, you can compute higher order cumulants. For example, I can compute the third cumulant, and that is basically its formula. Third cumulant and the fourth cumulant can be written as I will leave this as a derivation for you to do at home. Okay. You can write this as the third derivative. You can start the derivation with the third derivative of the moment generating function, cumulant generating function, taken at k equals to 0, and this can be written as x cube minus 3 mod x mod of x square minus plus 2 times mod x cube. Okay. And this quantity has a significant meaning or significance in statistical mechanics. This is called as the skewness of a random variable. It will tell you whether the distribution is skewed towards a positive tail side or a negative tail side. And finally, one more moment I am going to write down, which is the fourth cumulant. And if you derive this, its expression would be x to the power 4 mod x 4 minus 4 times mod x cube into mod x minus 3 x squared the whole square plus 12 mod x square into mod x the whole square minus 6 mod x to the power 4. And this is called as kurtosis in statistical mechanics. Okay, we will give some examples in the tutorial to explain what is what is the physical meaning of these cumulants. But it is usually enough to stop at the fourth cumulant, and one usually does not go to cumulants beyond order 4, because all the information that one usually needs is available with these 4 cumulants. So, it is enough to, in most problems, to go up to the second cumulant, and in problems such as fluid mechanics, one can actually compute cumulants up to order 4, which will give important information about physical properties of the system. So, this is the basic idea behind deriving these moments and cumulants. So, what we have, if we summarize everything, what we have seen so far is basically a moment generating function. So, if you want to generate moments, then you basically use just the characteristic function, which is the Fourier transform of your PDF, or if you want cumulant generating function, then you can use a logarithm of the characteristic function. To generate mth moment, you have to take the mth derivative of this characteristic function at k equals to 0, and to generate the mth cumulant, you have to take the mth derivative of the cumulant generating function. So, it is in some sense symmetric in its application. Fine. So, this is the short summary of what we have learned so far, and it is important to see that there is a very beautiful diagrammatic way of remembering the connection between moments and cumulants. So, just because this method is very eye pleasing and easy to remember, I will give you this exposition of how to diagrammatically connect moments and cumulant without going into too much derivations. Okay. So, the idea is to connect these moments and cumulants using some sort of a diagram, right. So, now the diagram is the following. Suppose I want to write down the definition for connection between first moment and first cumulant. Okay. So, if you have a first moment, okay, so I am going to write down moments here on the left hand side, okay. So, let me just rub all this and write down in some sense. So, I am going to write down moments here, I am going to write down cumulants here. Okay. So, write down the first moment. Yeah. So, the first moment is actually, you can use, for first moment you can use a single dot. The number of dots is equal to the order of the moment. Okay. Now, the first dot you can only show by, you can show the dot as is. You cannot, if you have more than one dots, you can connect them or you can leave them disconnected. So, in case of just a single dot, there is no logic, there is no point of connection or no connection, you just leave it as is. Okay. To connect dots, you need at least 2 dots. So, the first moment is nothing but the first cumulant itself. That is the idea. Okay. So, I am going to write it as just the first cumulant. Now, to second moment, I have to take 2 dots, but I can write down 2 dots either disconnected or I can connect these 2 dots. There are only 2 ways, okay, leave them disconnected or connect them. So, this is the interpretation. So, if you leave them disconnected, this is nothing but the moment, but it is squared. How many dots you have? This is basically 2 plus the connected dots are the second cumulant. Okay. Maybe this is better if I write it below. Okay, so I am going to write it below it, just so that okay. So, maybe it is better that I write them below the dot. So, the first moment is just a single dot and that is nothing but the first cumulant. And what we had just shown is the second moment. So, for the second moment I need 2 dots. Okay. As I said, the number of dots taken should be equal to the order of the moment, but I can take 2 dots and also connect them. Okay. So, if you leave them, it is called as the second power of the first moment, and if you connect them, it is the cumulant. Okay. So, the logic here is unconnected dots are moments, okay, and connected dots are cumulants. Okay. But I know that the first moment is also a first cumulant. So, this is also a cumulant square. Let us go towards the third moment. Now, for third moment I need 3 dots, okay, because I said that number of dots are equal to the order of the moment. Now, with 3 dots I have 3 different possibilities. I can leave all of them unconnected, or I can connect 2 of them and leave the third unconnected, but there are precisely 3 ways of doing it. Okay. So, I can leave this dot and connect these two, or I can leave this dot and connect these two. So, there are 3 ways. So, this 3 basically is written precisely to account for the other 2 ways. Okay. So, I am going to rub all this and write down 3 times this plus I can take all of them together. Okay. There are no more ways to it. So, if you take 3 disconnected dots, this is nothing but the cube of the first moment, okay, but the moment is also equivalent, plus 3 times this is nothing but the second cumulant, because I have connected 2 dots into the first moment. This third dot is empty, is disconnected, but I know that the moment is also equivalent. So, you write it as a first cumulant, and the final configuration is basically the third cumulant. So, that's how you write down for the third moment, x third cumulant plus 3 times second cumulant into first cumulant plus the third cumulant. Similarly, you can write down for the fourth moment as, for the fourth moment I need 4 dots. Now, how many ways can you arrange 4 dots? Well, you can leave all of them free or disconnected. So, this would be the first moment to the power 4, but I know the moment is also cumulant. So, you can just put a 4th power of the first cumulant. I can connect 3 of them and leave the third guy. Okay. But precisely there are 4 ways of doing it. So, this is nothing but 4 times the first moment into the third cumulant. I can pick 2 of them and leave the other, okay, and these are basically 4C2 ways, which is 6 ways of doing it, okay. So, this is 6 times second cumulant into the square of the first cumulant, plus I can pick 2 and also pick the other 2. Okay. There are 3 ways of doing it. So, I am going to write 3 times second cumulant square, because each one of them is a second cumulant. So, this is a square of second cumulant. Now, how can I do it 3 times is basically one, if you want to see how can I do it 3 times. So, this can basically mean that I can take it like this, I can also take it like this, I can also take it like this. That's it, only 3 times. Anything else would be a repetition. So, that is why this is just 3 times of second cumulant square. So, as you can see, this is a very nice diagrammatic way of constructing the relationship between moments and cumulants, and a very powerful method that I have stated without any proof, but the proof is also straightforward. It is just comparing the moment generating function and the cumulant generating function and comparing terms of equal orders, which will lead to this derivation, which will lead to this formulation actually. So, we stop this lecture at this point, and we will continue from the next lecture and derive some characteristic functions of important distributions in statistical mechanics, such as the Gaussian distribution, the exponential distribution, and the Poisson distribution. So, when we come back here next lecture, we will start off from some very important distributions that are found in statistical mechanics, and we will proceed from there.